Is the universe destined to be filled with isolated supergalaxies? Will gravity continue its unending pull? To find the answers, we enlist supercomputers as time machines, taking us into the future. The scenario they predict may be far more grim than anyone ever suspected. The world's greatest telescopes and satellite observatories routinely serve up awesome pictures of cosmic clusters. But essentially, these are only snapshots in time. To truly watch the universe as it evolves, we need a time machine.
Human lives are short compared with cosmic timescales, but we can watch effectively how galaxies and galaxy clusters evolve by simulating them on powerful computers.
The supercomputer turns our starship into a time machine for the next leg of our mission, to find out how the universe evolved and where it's going to end up. This simulation shows how a galaxy cluster may form. 12.3 billion years of stellar evolution is condensed into less than a minute. Supercomputer visualizations like these are important tools to help all of us understand the workings of the universe and where the future will take us.
The simulations where we can actually play how a galaxy cluster evolves over billions of years always leave me breathless. It's amazing to watch cosmological time play in these beautiful, elegant simulations.
Here's how the supercomputers do it. They start with something that scientists call the N-body problem. N stands for the number of bodies. The bodies are planets, stars, or galaxies. And the problem is to do some simple math to figure out how Isaac Newton's basic laws of gravity make the planets or stars move in space.
Such simulations are remarkably powerful ways to study how complex systems like clusters of galaxies and galaxies evolve with time.
Peter Toobin, a simulation specialist at the University of Maryland, programs the gravity formulas into a supercomputer named Deepthought. It's easy, for instance, to figure the orbit of a planet around a star. That's called a two-body problem. A college math student can do it in a snap. But suppose you have to work out the motions of a swarm of stars in a star cluster.
The n-body problem is a little bit like a juggling act. If you have a two-body problem, here we have one ball. I can do one ball relatively easy, but I'm not a juggler. I don't know if I can two balls. Oops. Well, clearly I cannot do two balls. And it takes a lot of effort and interpretation by the brain how to correctly juggle two balls. Now imagine that we have to do three balls or four balls. I cannot do that. There are people who can do that. But the complexity ends at some point. Nobody can do 20 balls.
Surprisingly, the math behind the problem is fairly easy. But the reason you need a supercomputer is that there's just so much of it to do. It's pure grunt work.
All right, guys, ready your position.
As Toobin's students demonstrate when trying to do it for 12 stars without a computer.
Number 1 is at 6-4.
Number 2.
2 is at 3-4.
Number 3.
3 is at 2-4.
In calculations like these, each star's starting position gets coordinates on a chart.
Number 8 is at 4-4.
Each star also gets its own speed, and the rest is up to the students. Using Newton's laws, they have to figure out how each star's gravity acts on each one of the others to determine where each star's position will be at the next point in time.
Number 1.
These students would need to work for 300 years non-stop to do what a supercomputer can do in 1 second. Calculations for galaxy clusters ramp up to millions, even billions of n-bodies. But fortunately, supercomputers are increasingly available to astronomers, eager to simulate the past, present, and future of the universe.
The current state-of-the-art supercomputers are actually off-the-shelf computers that you and I use at home, desktop computers. The only thing is we put them all together. They're easy to build, they're cheap to build, so there's many available.
Among the most complex of the current simulations is the Millennium Run in Europe, where 10 billion galaxies were manipulated in a supercomputer running continuously for 28 days, utilizing 343,000 processor hours. One result is a remarkable 3D fly-through across 2.4 billion light-years of space, showing hundreds of millions of galaxies clumped together in clusters along vast strands of dark matter. Using supercomputers, scientists not only study the past, but they can predict the future of the universe.
I think it's amazingly cool that we can actually take what we know about the present-day conditions in the universe, and we can basically use these computer simulations to play time forward. We can use this to extrapolate what's going to happen to us in the end.
This simulation starts with the quantum foam left over from the Big Bang and flies us through 13 billion years as it all condenses into the galaxy clusters and superclusters along the network of filaments and voids, like those we can detect today. This is the cosmic clustering phenomenon, driven by gravity to its greatest extreme. But gravity's pull is counterbalanced by the mysterious dark energy that is driving the galaxy clusters of the universe apart.
About a decade ago, astronomers discovered that the universe is not just expanding. In fact, its expansion is accelerating with time.
Gravity will keep galaxy clusters together only on a local level. Our local galaxy group will coalesce into one super galaxy, but all other galaxies in the universe will race away from us. 100 billion years from now, this corner of space will be left virtually in the dark.
As soon as the distant galaxies around us will expand away and reach the speed of light, even light from them will never be able to reach us anymore. And so these galaxies will expand into vast regions of space and disappear from view. Our galaxy will be an island embedded in darkness.
Clouds of gas will continue to form into star clusters nearby, but astronomers of the future will see nothing in the sky beyond the borders of our own galaxy. Unless the work of today's cosmologists is preserved, there will be no clues to tell them that there was once a Big Bang and a cosmic expansion.